Today we are going to discuss a new chapter, probability. Probability is the study of randomness. In this chapter we are going to discuss several topics which are divided into several units. The first one is randomness. The second one we are going to discuss probability models, including sample spaces, and we also discuss several very simple probability rules. The next topic is random variables, and then we are going to learn how to calculate the means and variances of random variables. We are going to discuss discrete random variables and continuous random variables and the normal distributions and the means of random variable and some others. The last topic is general probability rules. Those are more advanced than the simple probability rules. The first topic is we are going to clarify several basic concepts. The first one is random. In the previous chapters, when we try to design experiment, we always emphasize that randomness is very important. So what is exactly a random? A phenomenon is random if individual outcomes are uncertain, but there is a regular distribution of outcomes in a large number of repetitions. In this example, the x horizontal is the value that the outcome can take. For example, the IQ scores or the GPAs or ages. The vertical is the frequency or the occurrence of the variable or of the outcome at a particular value. For example, if the IQ equals 140 or some 135 or something, so how many people are have this IQ score? For a large number of repetitions, that means the number of people is large, or the test, that means that the test is very large, then the outcome we can see follows some regular distribution. In this example, it looks like a normal distribution. So each outcome is uncertain. For example, when we toss a coin, we know there are two possibilities. One is head, another one is tail, but we don't know exactly which one is. But what we do know is if we toss this one for a many times, then the probability of the occurrence of head and tail most probably will be 50-50. So then this is the toss of a coin is a random phenomenon. The next topic is probability. So what is a probability? The probability of any outcome of a random phenomenon can be defined as the proportion of times that the outcome would occur in a very long series of repetitions. We still use the example of the coin toss. For example, we toss the coin 100 times. If we count how many, we are going to count how many heads we have. Suppose we have like 49 heads. Then the probability will be 49, which is the proportion of the times of an outcome, which is the head occur 49 times. In a very long series repetitions, here is equals 100. So 49 divided by 100 equals 49%. So that is the probability for the coin, for the toss of a coin to be a head. Sometimes 100 is not large enough. You may want to 1,000 or 10,000 or even larger. So that depends on the problem. The next concept is called the independent event. We said two events are independent. The meaning is the probability that one event, for example A, occurs on any given trial of an experiment is not affected or changed by the occurrence of the other event, for example B. Now, for example, if we have a coin toss and we toss twice, the first time is event A, the second time is event B. We toss the same coin. So what is the probability for event A to be a head? That's 50%. Then we toss the second times that event B. So what is the probability for it to be a head? So, because these two, we use the same coin, so we can assume the probability will be the same, still 50%. Then we call these two events are independent. Two events are not independent or called are dependent if the probability of one event, for example A, will be affected or changed by the occurrence of the event B. For example, if I have a bag of balls, right? We have 100 white balls and 100 black balls put in a bag. We cannot see what is inside. You randomly pick one outside. What is the probability for it to be a white? We know there are 100, 100. Then, so the probability equals 100 over 200, so equals 50%. So this is event A. Event B is you pick another one, a second time. What is the probability for the second time you choose the ball? It is a white. Now, these two events may be independent or may be dependent. Depends on how we choose, how we pick the second time. If we, in the first time, we pick the balls, then we just put back. Then we pick the second time. Then these two events will be independent. But if we pick up the first ball, then throw it away, do not put back in the bag, then we try to pick the second one. That is, if we call that is event B, then event A and event B will not be independent. It will be dependent. The chances for event B to be a white depends on event A is white or black. Later time we are going to learn how to calculate this in details. Again, we take this example, the coin toss. The result of any single coin toss is random. We don't know it's the head or it's tail. It's 50-50%. But the result over many tosses is predictable. And if the coin is irregular, then we can assume the result will be 50-50%. As long as all the trials are independent, which means the outcomes of the new coin flip is not influenced by the result of the previous flip. In this example, here, for example, if we only toss once, this one, the x horizontal is the number of tosses, the vertical is the proportion of a head. So we are interested in head. So if we toss the first time, looks like it is a tail. So the proportion of the head equals 0, 0 over 1. Then we toss the second time. Looks like the second time it is a head. So now for the first two times we have one head, one tail. So this is the proportion of head equals 50%. So that it will be here. Then we toss the third time. Looks like it is a tail again. So the proportion of head will be 1 over 3, which equals 33%. Then the next one is looks like a tail again. So the probability will be equals 1 over 5. So that 1 over 4. So that is 25% here. All right, but so we can see the probability varies a lot at the very beginning. But if we toss number is large enough, 50 times, 100 times, 500, 1000, or 5000 times, so we can see the probability or the proportions of a head will very close to 50%. We call this converge to 0.5. Looks the probability is very easy to understand, but sometimes most probably it's not easy to understand. Sometimes it's very easy to guess. For example, the probability when we toss a coin to be a head equals 50%. So everybody knows this. Or if you want to have a baby, so the chances to have a boy and a girl, most probably again 50%. But sometimes the probability is not that obvious. There's a famous example here. It's called the Monty Hall problem, or it's also called the three-door game. This is very interesting. So we are going to discuss a little bit more with more details, and hopefully give you some. You will be interested in this. This game is a counterintuitive statistics puzzle. The problem is like this. We have three doors and labeled by 1, 2, and 3. Behind each door, behind the three doors, we have two goods and one car. We know the car is much more expensive than the good. So you want to pick one door, and no matter what is behind, is yours. If the behind the door is a car, then you get the car. If it's good, then you get the good. So everybody hope to get the car. Now how we play this game? First line, you choose one door. Suppose, for example, you choose door number 1. Now the host, Monty Hall, open the one. Look at the other two. So number 2 and number 3. Look at this. Once you choose one, then the other two cannot both have cars because there's only one car. So at least one of these is good. So he look at the behind of these two doors and open the one with the good. For example, if this one is good, if this one is the car, then he opens this one. If this one is the good, this one is the car, then he opens this one. If both are goods, that's possible because the car may be in the first one. Then in that case, he just chooses any one, so open it. Okay, now here you need to choose. If suppose he opens this 3, now you have an option. You have two options. You can stick to your original choice. Okay, you said I still choose one. Or you said, okay, I change my mind. I want to choose the second door. The question is, do you want to? Once you see he opened the door with the good, suppose in this case he door 3. Do you want to change your choice from 1 to 2? Does this make sense? Make sense means increase the chances you win the car. Okay, now let's think about this. If you have two options, you can stick to it or you can change your mind. If you stick to it, so definitely your chances to win the car is 1/3. Because when you choose door A, we don't know which one has the car. So you just randomly choose one, suppose A, then the chances for it has a car equals 1/3, so it's 1/3. Now, that means if you after you see this good, you still stick to one, then your chances of winning the car is 1/3. But you have 2/3 of chances to lose the car because the car may be here or maybe here. Let's see if the car is here. Then, when he opens this door, if you change your mind, you choose this one, you get the car. Okay. Now, suppose the car is here. Then we know he will open this door. Once you see the good behind this door, you change your mind, you choose this door, okay, now you get the car. The only situation when you change your mind but you still lose is when the first time you choose this one and it has the car. So that means if you do not change your mind, you have 1/3 of chance winning the car. But if you change your mind, you switch to the other door after you see the good, you have a 2/3 chance to win the car. So that means you need to switch. So think about this. Mathematically, looks like this is correct, but you still cannot imagine why do I need to switch, because I don't know which door has the car. Now you think about we have 100 doors or 1,000 doors. Again, there's only one door has the car. All other 999 doors have the good. What you do is you choose one car, you choose one door, then we know the chances for that door have the car is very, very small. It's 1 over 1,000. Then Monty Hall opened the other 998 doors that have the good. Then the other one, you think about this. Should you switch to the other one? So now definitely you understand we need to switch to the other one, because the chances for the first one to have the car is only 1 out of 1,000. So that means the cars most probably will be in this 999 doors. And he opened 998 of the doors. All of these doors have the good. Then definitely the other one. We cannot say definitely, but most probably the other one will have the car. So the probability is much, much larger than the first door having the car. So now I hope you will feel better. So now, from mathematically, we know, okay, we should switch. And from this extreme situation, if we have 1,000 doors, we are convinced that we should switch. But, so looks like the problem is very clear. So we should switch. So why do we need to switch? Because at the very beginning, we think each door has 1/3 of chance of winning the car. So why you want to change is not 1/3. So what's the problem here? Looks like a random. Each one has 1/3. So why it is not 1/3? The question is here. Monty Hall changed the problem. He looked at the door and opened the one that has the good. So that means his action of open the door is not random, because he already knows which door has the good. So there's extra information inside here. That means all these events are not independent. So it's not 1/3. If we change the rules of the game, for example, if you choose any one, for example, door A, door 1, the first one, and Monty Hall does not look at the other 2 doors. He just randomly, we do not say open it, it's randomly reserve one. Then, for example, reserve 3, but still won't let you see. Do you want to switch to the second one or not? So in that case, it doesn't make any sense to switch to second one, because Monty Hall doesn't know this door has good or not. So the probability for each one has the curve is still 1/3. So we do not have extra information involved. So all the events are totally random, independent. This example to show you that probability sometimes is very simple, it's very straightforward. Sometimes it's not that obvious, but hopefully you will agree with me that probability is very interesting.